did say he was. Yeah. Okay.
Okay.
All right.
Microphone.
The mic.
Yeah.
Yeah.
So welcome to our next speaker, Ramon Egli, who's going to talk about not just FORCs, but beyond FORCs. So, thank you, Ramon.
Okay. Thanks. Just a few words before I first met Eston and Dunlop in person at the KJS meeting, so one of the Santa Fe meetings. And we have they were very nice with me and my wife, young scientist at that time. And we have my wife also good rememberings of that time. And so thanks for that. And so now I will switch a little bit the topic and we'll go a little bit away from my obsession for diagrams and become even worse. So how do you? I don't see the control buttons to the arrows. Okay, the arrows. Okay, so actually, these people here brought me to the idea which I'm presenting today. So I am very grateful to them to have triggered that. So I will start with a quiz, a provocation, and ask you, what is this? What mineral is producing this? What type of parting is producing this? So probably this is a rhetoric question, so nobody dares to answer. So I answer, I spoil myself, and this is actually synthetic ultrafine magnetite in the SPSD range, undiluted, so just as it has been synthesized in aqueous solution. I think I would never say that from the corresponding FORC diagram. So I will never stop to stress that we still have ambiguities in interpretation of magnetic measurements, and this will probably be something that never goes away. But nevertheless, we can keep trying to get more information out of our measurements. And one thing we should never forget when we measure FORC diagrams is that we actually are looking, the FORC function, we are looking at the summation of three different processes: instantaneously irreversible magnetization changes that occur while we are sweeping the field, time-dependent irreversible processes, that is the magnetic viscosity is not present only in the vertical reach, it's present all over the FORC space. We just don't realize it probably. And we have reversible changes. And all these overlap, and sometimes they overlap so that they cancel out each other. So this makes interpretation not so easy. And actually, Zhao and others in 2017 devised a modified protocol which can distinguish between irreversible and reversible contributions. And this happens by, instead of sweeping the field from the reversal to field to saturation continuously, you just at every step go to zero and measure a magnetic remanence. That way you get away from the induced part of the magnetization. Of course, nominally, you are getting also away from first order reversal curve, because the zigzag thing means that you are measuring higher order curves. Nevertheless, you get irreversible changes in the transient region, these two triangular regions colored in red. You get something in the memory region, and you get the induced part. Okay, so this is running successfully. So and I was planning to do something similar, but actually the sample I was interested in had some strange features occurring at the boundary of the memory region. And now the problem with this protocol is that it introduces little discontinuities at the boundaries of the memory region, because that's the place where the protocol is changing. So you are changing this field sweeping direction. So, and therefore the questions I asked to myself is if it is possible to do something similar but locally. So you don't get away from your FORC trace, and you just try to disentangle these three contributions locally there. This is a non-local method. I was thinking, is there a local method? But I already anticipate yeah, there is a possibility to do it differently, but not for the entire FORC space. So this will remain a standard procedure if you want to map the entire FORC space. But if you want to know something special, more detailed in certain regions, then there is another way to do it. So this is the outline of my talk. So I will first of all present the protocol, which consists in adding a Rayleigh loop, basically, to the measurements. And then I show 3 examples from the most textbook-like one to a more practical one. It has to do with soils, and then we get a little bit to the field that Hudson was also investigating. So basically, what you see on the left diagram is if you would do a conventional FORC, you would just sweep the field in positive direction in a continuous way. So the modification consists in stopping at each step and actually make a Rayleigh loop measurement. So sweep the field back and forth with a small field amplitude delta B, which in the data I will present here is 0.5 millitesla. And so what you see when you start the very first point, and then you do the first Rayleigh sweep, that's the first time the sample is seeing this larger field, this slightly larger field. And so you will introduce irreversible changes in the magnetization. But once you have done this step and you go back and forth in the successive cycles of the Rayleigh loop, you will induce reversible magnetization changes. So you're basically measuring AC susceptibility. But because the VSM is not really an AC machine, you have to give commands. You can do this with the scripting language and let the machine really go from one point to the other in sweep mode. So that takes more time than doing a real AC measurement. So usually I use 20 cycles, that takes a minute or so. During this time, of course, the sample is in a DC field, and it will change its magnetization viscosity. And viscosity is not only in a single domain range, so you will have always some viscous changes during the time you're measuring your 20 Rayleigh cycles. So when you're finishing cycling at one step, one field of the FORC, you go to the next one and you repeat the procedure. And this is the same thing shown as a function of time. And so the 3 contribution comes up more clearly, the initial increase, irreversible increase, then you have this drift due to the viscosity and the sawtooth pattern that is superimposed. The amplitude of this pattern is the reversible magnetization change. And actually, to disentangle this 3 contribution, you need to fit viscosity to model viscosity, and this can be done with the usual logarithmic law. And so you get your 3 contribution separated at each step. So there is a little complication to that at the reversal field. Usually the reversal field is a troublemaker, and this is because when you arrive at the reversal, you sweep your field from positive saturation towards negative, and so you get a viscosity in the reverse direction. So this is producing a sagging that is also seen in the traditional FORC measurement, and that gives you the vertical ridge as it was discovered by Chris Pike in 2001. And this process continues for the first initial steps of the FORC measurements. So also the next one will be a little bit affected by this decrease, but then eventually the increasing of the field during the FORC measurement will take over, and you will have the normal viscosity again. You see this better in time. You have this initial decrease, you have a mixed situation, and then you get to the usual viscosity. So when you fit the first steps, you have to include both viscosity changes. And one interesting thing that you get out of these measurements, gratis, is the so-called fluctuation field. This is defined as the viscous coefficient being equal to the irreversible susceptibility, so the irreversible magnetization change divided by the step. The field step, this is the fluctuation field. You can imagine the fluctuation field as the difference between the field that is required to switch a particle without thermal activation and with thermal activation. That's more or less the fluctuation. And also for an assemblage of randomly oriented Stirling-Wolfram particles, the fluctuation period is inversely proportional to the volume of the particles and is weakly correlated to the so-called micropercussivity. That's the anisotropy field of the particles. So this will become useful in the later examples. So let's start with a textbook example. My favorite, magnetotactic bacteria. So as you know, these chains of magnetosomes have an ideal behavior, the ideal behavior of uniaxial single domain particles. So in the FORC diagram, we have this central ridge, and we have below this pair of negative and positive contributions, which corresponds to the reversible rotation of the magnetic moments in the field. So this is our reversible contribution to the FORC diagram. The central ridge is irreversible. But if you have a little bit of FORC eyes, you will notice something strange. Yeah, you get this diagonal thing here, which should not be there. So there is a slight increase in the negative positive averages out there, which does not occur if you measure other strains of culture. They are all cultural, they're not wild type, magnetotactic bacteria. So there is definitely something particular going on there. So, and maybe the new protocol will be useful to understand what is going on there. I also spoiled already my results by giving an interpretation that will help understand the results of the measurements actually. So in this case, you choose one or two curves that you want to measure and they cross the area of interest. So in this case, this diagonal. Yeah. So you run through this period feature and you will see what is creating it. So the particularity of this particular type of magnetotactic bacteria when they are grown fast in the laboratory is that they, the bacteria make a template with the membranes that will be filled by magnetite, and this will built along a string. The particularity is the nucleate magnetite grows randomly. So they grow fragments of chains initially, and sometimes we have isolated magnetosomes forming along the chain axis. And actually, this magnetosome is not really isolated. It is feeling the stray field of the chain. So this is a case of positive magnetostatic interactions, which are not very common, let's say. And what happens is that, for instance, when you measure this curve, you have a small reversal field. Most of the chains will be positively saturated chain fragments, so they give a positive field, bias field, when the isolated magnetosomes are switching. And the isolated magnetosomes are equidimensional, they have almost no percussivity, so they switch in the zero field, and so they will see this bias field. And when we go to a more negative reversal field, this switching occurs when more chains are already negatively saturated. And so the switching field of the isolated magnetosomes will be a little bit different. So if you subtract one curve from the other, which is what you have to do to calculate the FORC function, you get a step along the diagonal. So that's the interpretation. But of course, that needs to be verified. And this is nothing new. Gary Acton, back in 2007, described something similar. This diagonal feature here as the result of interaction between a magnetically hard and a magnetically soft phase. And here we have something similar. So now let's go to the FORC Rayleigh measurements. You see on the top. Okay, it's coupled. So the green curve are the reversible magnetization chains. Notice that they have a peak at 0, so the discontinuous first derivative. So this is the problem in processing as usual. Then the orange curves, these are the viscous contribution. That's the dominant contribution there. I thought it's okay. And then you have the red curve. That's the irreversible, instantaneously irreversible magnetization change, which is the smallest one in this case. So this is a zoom of the above measurement on a smaller field region. You will also see that this of course, the switching of the chains stops at minus the reversal field because you have switched them all to back to positive saturation, so nothing happens beyond that level, which means nothing happens above the central ridge. In this case, you'll see the fluctuation field on the right. It's about in the area where the chains switch, in the field range where the chains switch, it's about 2.53 millitensor, which is normal for these particles. But very interestingly, you see that at zero, so where the isolated magnetosome switch, the fluctuation field is significantly smaller. So there are only two ways to make it smaller. Either you have a larger volume, but these magnetosomes do not have a larger volume, or you have to massively decrease the micropercussivity, and that's the correct answer. These particles have basically no anisotropy, and this causes the decrease in the fluctuation field. So when you make the difference between these two curves, you get FORC, and you see the central ridge. This peak is the central ridge, and you see that central ridge contains equal amounts of irreversible, instantaneously irreversible, and viscous magnetization changes. Now, if you concentrate on the B equal to 0 region, you see that there are two types of contribution dominating there: the reversible contribution and a viscous contribution. And the sum of the two is giving this step that is then seen in the FORC measurements. So now we run to a slightly different example. This is a rhyolite, which is a rock contains in fine-grained magnetite. And you also see here the central ridge, the upper part of the FORC diagram has this traditional triangular shape. Control line, nothing special, but here again you see it's a strange, unusual feature in the lower half of the FORC diagram. This clear jump occurring along the descending diagonal that needs again in zero field. So zero field is a particular region in many cases. So here I measure two FORC curves at starting at minus 50 and minus 75 millitesla. You see in green again the reversible magnetization change, in red the instantaneously irreversible, and in orange the viscous one. And a particular thing, the noticeable thing here, is that both the irreversible and the viscous changes start abruptly at zero. And actually this means that there is peak there. This means that there is a significant amount of particles that switch exactly in zero field. You could say, well, that's normal through thermal activation. But this happens also for irreversible, so non-viscous magnetization changes. On the top of that, if you try to simulate these curves using Stoner-Wolfram particles with a certain with a broad distribution of volume as we have in nature, and with a certain distribution of micropercussivity, you will never get this sharp transition here. So the curves will always have central peak at zero, but they will be broad. So in order to get this sharp onset, which is also seen here in the FORC diagrams, you need to assume that there are particles with zero micropercussivity. And actually, for magnetite, this is not expected really, because magnetocrystalline anisotropy will always be there, but probably there are different sources of anisotropy from irregular shape, magnetocrystalline, and maybe surface oxidation that can combine in a way that certain particles have virtually no anisotropy, and this could explain the data. This is the fluctuation field, and this is the FORC, and in the region near E equal to 0, you see again the step here, and you see the central ridge. So now we move to something more interesting, pedogenic magnetite. So this measurement corresponds to the difference between the measurements of a paleosoil, untreated paleosoil, one of the strongest from the Chinese plateau, I think this one, and the same sample after a leaching procedure that removed predominantly single domain particle, namely the CBD extraction method. So the difference between these two measurements is giving the in situ properties of the fine particles that have been chemically removed. And what you see here is there are two main features here, there is the central ridge, which correspond to well-dispersed particles in the soil matrix, not magnetozones. We know that from the distribution. And we have all this contribution around the central ridge. Notice that you need to represent the FORC diagram correctly to see this, otherwise it will almost be invisible. But this other contribution, which could look like vortex particles, or as clusters of single domain particles, who knows, they contribute about 50% to the sample. So it seems that there are two types of particles here representing the pedogenic contribution. And the question is, what is the nature of these two groups of particles? So here I have chosen 4 parts where I did these new measurements. And you can see again green the reversible magnetization changes, and in orange and red the viscous and the irreversible parts of the magnetization changes. And in all the curves and in all field ranges, the viscous contribution is dominant. So that it is dominant over the area affected by the central ridge. So between 0 and minus the reversal field, this is normal. This is the switching of fine single domain particles, which we know they are viscous. But what about this part here? So this central ridge particle now have been switched to vector separation, to positive separation, and we still have the same ratio between viscous and non-viscous contribution, exactly as for the central ridge. So it seems that the entire area of the FORC diagram is presenting the same relative amount of viscosity. So if you interpret this non-central ridge contribution as coming from single vortex particle, from my knowledge, you should expect a difference in viscosity. Maybe Wim will step in and say, no, I don't know, but I would expect it personally. And if you look at the fluctuation field, that's confirming what we have seen here. So you see practically that yes, in the range, field range affected by the central ridge, you have a slight increase in the fluctuation field and in smaller particles, but that's not dramatic. And especially not in the last curve, you almost don't see any difference. So the curve seems to be continuous, so there seems not to be any difference in terms of viscosity between the central ridge, or any massive difference between the central ridge and the remaining part of the diagram. So this is showing that we have two groups of particles that both behave in a viscous manner, and probably the only interpretation right now for me is that one is a group of particles that is well dispersed in the same matrix, and the other one are clusters that produce this vertical spread because of magnetostatic interactions. Now, if you look at the residue, so what remains after extracting the fine fraction, you see this classical PSD signature now, and there I run the same four curve through it. And you see that the situation now is drastically different. Now you have almost equal amount of viscous and instantaneously irreversible contributions. Okay, so that means viscosity is much less important here, which can be expected, but it's not zero. So there is always a little bit of viscosity. And this is the fluctuation field in brown, the fluctuation field obtained from the pedogenic particles, and in yellow, the one obtained for this residue of the extraction. And you see that they have opposite, they are very different, first of all. And secondly, they have opposite trends. So in the pedogenic fraction, the fluctuation field decreases as the coercivity increases. So large coercivity particles, which are probably most elongated, have a larger volume. This makes sense. While if we look here, we see that the fluctuation field has a slight increasing trend when we go to larger coercivity, and this corresponds to the fact that the contour lines are making a transition from typical PSD triangular pattern to a more SD one as we move to higher coercivities. So this is also a coherent pattern. And so on Monday, I was mentioning these results to Roger Cook, and he said, oh, actually, I have scanned a soil sample, and I have found that there are regions in the soil sample which contain clusters of ultrafine particles. You see those clusters here in SEM. You can vaguely imagine the individual particles in these clusters. And then I was very happy to see this because this could be one of the two pedogenic components that I was seeing with the FORC Rayleigh protocol. And actually, this also matches very well with the ARM ratio. So the ARM ratio of the bulk pedogenic component is almost what you would expect for non-interacting single domain particles. That's because of the contribution of the central rate. But the ARM ratio calculated with the scanning microscope on these clusters is a factor of 6 smaller. And we know that magnetostatic interactions, which are expected in a cluster, are depressing the ARM. So I think I could convincingly show you that there is definitively room for applications for this new protocol to understand more in detail what is going on while we are measuring, while we are doing FORC measurements. So thank you for your attention.
Well, thanks. Are there any questions for Ramon?
Sorry, I missed most of your talk the other day, but I have a very basic question. So if you are varying your average time in your FORC measurement, is that going to have a profound impact on what you see with the viscous component?
Yes, because you give more time for viscosity to run. And also if in this protocol you choose to measure, at the beginning I was choosing 100 Rayleigh cycles instead of 50 or 20. And so the viscous component became of course more dominant. So and eventually the irreversible part becomes invisible. So you have to choose the number of cycles so that you can see both.
So if you're measuring weak samples, is there going to be a trade-off between the amount of superparamagnetic material that you can resolve and the quality of the guide?
Yes. For instance, the averaging time is massively affecting the appearance of the vertical ridge. So that makes basically measurements of the vertical ridge difficult to compare among different measurements.
And is there any useful information by comparing, let's say, a FORC running a long time with a FORC with basically very, very small average time?
Potentially, yes, if you calculate the difference. Yeah. I never tried, I tried other things, but this could also maybe reveal some. But you have to reduce the noise very much because the difference will be tiny. So
okay.
Yeah.
Thank you very much.
Thank you.
Other questions for Ramon?
There are a couple of online comments. As there are a range of low energy barriers for single vortex states in irregular grains, that we might expect to have viscous signature that is different to the sample single domain logarithmic signal. And then Nono Lasku writes in, without the CVD extraction, how would you separate the contributions of clusters from that of larger particles?
Yes, this is a good question. Actually, in this particular soil, the pedogenic fraction is anyways dominating, so you would still see it. But let's say if you have a 50-50, that becomes really hard, of course. That's true. But one could do FORC Rayleigh PCA.
Any questions? Well, maybe we can head to our coffee break. If you have questions for Ramon, you can ambush him during coffee. Thanks again, Ramon.